So we're back discussing spectroscopy, in particular mass spectroscopy and the mass spectrum. And in the previous video, we were discussing alcohols, right? We said, hey, we've got an OH group on molecules, and we want to know how these things fragment off into pieces. And we kind of said they did homo and hetero both, but the hetero version had something in particular. Yes, we can cleave that bond off of there. And this is the molecule that we have left behind. However, the OH is not going to go off on its own. The OH is actually going to react and pull off a hydrogen off of a gamma carbon. And that's going to make water. And that's why we see this minus 18 formula weight show up very often in the spectra of alcohols. All right. So now I want to go back and I want to kind of just do a review. And here's an example problem. And it says primary alcohols have strong peaks of 31. What fragment's responsible for it? Okay, so a primary alcohol, what would that be? Well, let's say this is CH3, CH2OH. That's a primary alcohol, right? It's an OH attached to a carbon that's attached to at least one more. That's what primary means. Secondary carbons, of course, would be an OH attached to a carbon that's maybe attached to two other things. That would be secondary. Tertiary carbons would be or alcohols would be an OH attached to a carbon attached to three other things. So this is the one we're focused on. How do we get a formula weight of 31 from this thing? Okay, well, keep in mind that one of those possibilities is the alpha carbon, and the alpha carbon will cleave at that location. And in this case, let's say that it would cleave right there. So if it does, a double bond would form. This piece goes off. And we're left with this CH2 double bond OH group. Well, let's add this up. My carbon is 12. The hydrogen is 2. The oxygen is 16. And another hydrogen makes one more, which is a 3. Add them all up. There you go. That's where the fragment of 31 is coming from. Primary alcohols will always cleave with this specific piece in mind. That fragment's always the one that's going to be showing up. So if I see a 31 on a MS that's presented to me, one of the things that I could do if I've trained myself the right way is think, hey, this 31, there's no really other way that I could get a weird 31 number like this unless we have a primary OH group. Now, the secondary OH group's not so much, and the reason is because here's the alpha carbon. This would cleave one or the other bond, and we would actually have a bigger fragment that's left over, not a 31 anymore. Tertiary alcohol is the same way. Here's the alpha carbon. Once it cleaves one of those bonds, this piece is going to be much larger depending on what else is going to be present. So for that reason, only primary alcohols will really reliably give me this 31 because there's no other thing attached to those carbons other than the bond that we've cleaved. So that's the fragment that's responsible for the peak. That is a number that shows up very often, especially in the alcohol world. And if it does, it gives me an idea. We've got a primary alcohol on our hands. Okay, so with that said, we're going to move on to the next functional group. And the next functional group is going to concern something that we've talked about in infrared. All of these functional groups we've talked about in infrared. We're not going to talk about all of them, though, in mass spectroscopy. But this other one is kind of particular. And the functional group we're going to focus on now is going to be a ketone. So the ketone functional group, just in case you've forgotten it, is a carbon double bonded to an O with at least a carbon on each side of this. That is what makes this a ketone, right? So again, this particular bond right here, the C double bond O, that is what we refer to as the carbonyl bond. But in particular, if we have a carbon to the left and if we have a carbon to the right, that is the ketone functional group that we're referring to in this lecture video. So ketones have a particular way that they like to fragment. And what they do is that they take a look at this carbon, and you can almost call this the alpha carbon if you wanted to, right? So this is the oxygen, it's attached to the carbon. We can kind of call that the alpha carbon, and we can look at this location to kind of make that determination of what fragment is going to happen. Just like before in all of the other alpha carbon cleavages, we can cleave to the left or cleave to the right. What they do is that if they're given this option, they're going to form the most stable fragment. So again, that is no surprise. The most stable fragment. We just have to figure out really which one is going to be the most stable. The difference here, though, is that ketones, depending on the structure, can actually form a 6-member ring. None of the other ones have really done that. So this is almost like a complete reorder of the molecule. So we're going to have to talk about how. How does this happen? How does it rearrange to give me this ring structure that wasn't there before? This reordering, it has a special name to it, and this is called the Mec-Lafferty Rearrangement. So ketones can cleave like you would probably expect after you've seen the halogens, after you've seen the alcohols, after you've seen the ethers. I mean, this is an oxygen again, right? So they would cleave as you would expect, but they also do something in particular, and that particular fragmentation pattern is something called the Mec-Lafferty Rearrangement. So let's take a look at a compound. Let's say that we have CH3, CH2, CH2, C, double bond O, CH3. And this molecule is going to fragment, and we want to know how will it fragment and what kind of peaks would we see on a mass spectrum. All right, well, this molecule goes through the electron beam. It gets slammed with the energy. A tooth gets knocked out, and then the molecule can decide to break up into a piece. What piece would that be? All right, well, just like before, here's the alpha carbon. Option number 1 is to go through and cleave it off in that location. So what we would have is a CH3, a CH2, a CH2, a carbon with a double bond O, and a CH3. Like all of the other alpha carbon fragmentation patterns, when this bond cleaves, this is almost like a homolytic cleavage. The electrons get sucked in, and we actually create a triple bond. No surprise there, right? And this is the piece that carries the positive. This is the piece that carries the negative, and this piece does not get seen by the detector. If you add this up, 12, 12, 16 plus another 3, this is going to be a 43 fragment. All right, well, that's one option. Okay, so let's do the second option because we know they're all going to happen. It's just a matter of which one's going to happen more, but they're all going to happen. It's going to cleave on this side of the alpha carbon. So now what we have left over is a CH3, a CH2, a CH2, a C, double bond O, and then a CH3 that's now been cleaved. This bond is going to break. homolytic cleavage is going to happen. Those electrons get sucked up to the oxygen, and we now have a triple bond that forms with a positive charge. If I add up all of these, 12, 12, 12, and 12, plus a 16, plus a 3, 2, and 2, I'm going to end up getting a 71. And there you go. Now, you're probably wondering, well, why does a triple bond happen? And, I kind of made a mistake here. I mean, I know that I've drawn the positive charge. It is a positive charge on this fragment. But, I try to be at least as close as I can. The positive charge is going to happen on the oxygen, not on the carbon. Carbon's got 4 bonds. That's why this forms a triple bond. 1, 2, 3, and 4. Carbon's happy. There's no charge on that carbon. Sometimes, though, I seem to put the positive charge where that bond was broken, and that's not really proper. The positive charge is happening up here at the oxygen. Same thing's happening down here, but I wrote it in the right place. So there's 2 fragmentation patterns, and that's why the triple bond is formed between the oxygen and the carbon. That allows carbon to have those 4 bonds that it wants. Now, the question is, which one of these is preferred? Right? So if I had a 43, and if I had a 71, and these were my 2 choices, the molecule's going to split, and I need to reason out, well, which one is actually going to be a little bit better? Maybe my gut is going to tell me, well, let's look at our choices. Here we see 2 fragments. Here we see 2 fragments. This is going to carry a negative, and it's just going to be a methyl group. This is going to carry a negative, and it's going to be a propyl group. If I had to put money on it, at this point, you and your interpretation, if you had to put money on it, you would probably say, well, maybe the 43 is going to be the priority one. Because when this molecule splits, this negative piece is to the biggest chunk compared to this one, right? And this can help stabilize that negative out without a problem. So maybe that's what goes on. Maybe I'll see the 43 as a base peak. Who knows? But that's something that we can keep in mind when we take a look at this mass spectrum. All right, now what about the Mec-Lafferty rearrangement? Well, that one I'm not going to draw for you. I've actually got that one on a slide. If I decide to draw it for you, there's going to be no way you're going to make heads or tails out of it. You can see my handwriting. So let me pull it up on the slide. And here's the Mec-Lafferty rearrangement. All right, so first, what I have to tell you is that Mec-Lafferty rearrangement will only happen if you have a particular type of carbon. So here's the oxygen that's double bonded to the carbon. This is the alpha carbon. That means, well, hold on. Let me erase that. That's normally the alpha carbon that we would talk about. However, in carbonyls, the alpha carbon really starts here beside of that functional group. That's why they talk about the alpha there. So don't get that confused from what we did back here. The reason that I did this on you is because that's typically how we've been looking at these pieces, and I didn't want to change that up. All right? The chlorine was attached to the carbon. The OH was attached to the carbon. The ether group, that oxygen, was attached to the carbon. Same thing is happening here. The double bond O is on that carbon, and that carbon's going to cleave to the left or it's going to cleave to the right. That's why I listed this as an alpha, to keep the trend going that we've been learning. However, in real organic, this one is a little different because the carbon is part of the functional group. That's why they treat it this way. And this functional group is attached to an alpha carbon. You know, this one would have been an alpha carbon too. They didn't label this one because that's where that stops. There's no other carbons after this one. So this doesn't really is going to be an area of concern with us. So that's really the alpha carbon. Here's a beta carbon. Here's a gamma carbon. And on this gamma carbon, the third one down from the carbon involved in the carbonyl, that third one down is a perfect prime spot. Again, location, location, location. And what it has is a hydrogen. So you're seeing kind of the curvy arrow mechanisms here. One of the electrons will pop off of this bond. That's why you see a single barb and not a double barb. This one electron that was left behind when the electron molecule got slammed, right, and the electron popped off, that will form a new bond. And that's what you're seeing right here. Well, this has one electron that's left, so that one electron goes inward toward that carbon. And this bond, the carbon makes the decision to split it in half and basically send one electron inside, and we form a extra bond between those carbons. So this bond gets cleaved, hydrogen gets attached. A double bond forms here to make this relationship stronger, and when it happens, this bond will cleave as well, and in it goes. So this is the fragment that is now left over, and that fragment weighs a 58. So this piece right here, that is representative of here in the Mec-Lafferty rearrangement. It only works, though, if you have a gamma carbon. That's why we did not pay attention to this side over here, because it stopped at alpha. There was nothing over there that would allow Mec-Lafferty rearrangement to work. In addition to that, let's say that there was more carbons, okay? So I'm going to kind of erase all of this mess that I've drawn over here. And let's say that there were more carbons attached to this thing. Let's just expand the chain out. No difference here. What would happen is that this bond would still cleave. That hydrogen would go on there. This carbon-to-carbon bond would also still cleave. No difference there, and a double bond would still form. The only issue is that this one of these carbons will carry with it 3 more. The whole thing has to come, right? So this would be 1, 2, and 3. There you go. Now, of course, that would not have a CH2 there. If it had more bonds all the way through, we would have to rearrange the number of hydrogens over here to make this make sense for everything to have 4. But you get the picture, right? It's going to take with it what's there. Only the hydrogen gets pulled off, and only the bond between the true alpha carbon and the beta carbon is broken. But that's why we've done that, all right? That's why this one is called the alpha carbon, not really that one. I used this one as the alpha carbon in my previous examples because that was the functional group that was attached to the carbon. And that's why I've started off the carbonyl the way that it did, so you wouldn't get confused. But in the Mec-Lafferty rearrangement, you have to keep in mind that carbon is the functional group. So the next one over is the alpha carbon, truly the alpha carbon, and that's alpha, beta, gamma. If it doesn't have a gamma carbon, Mec-Lafferty is not going to work. So here's an example problem. It says, how could their mass spectra distinguish the following compounds? And all of these are ketones. All right, so what I'm going to do is just do what I did before. We're going to start at one molecule at a time, and we're going to break it off into the fragments, and we're going to see what's going to be there. All right, so I'm going to start with the first one. And in the beginning, here's my C double bond O. We are going to treat this like an alpha carbon, just like always. So we're going to cleave that spot. A triple bond is going to form now, and that will give me the positive piece. So this piece is no longer important. So I'm going to add all of these up. All right, so I'll bring up the calculator so you can see that process happen if you need it. So 16, 12, 12, 2, 12, and 3. That gives me a 57. So there's one fragment. That's what I would see. All right, so I'm going to erase all of this. We're going to do it again. This time, C double bond O, I cleave on that side. This piece goes away. Oxygen sucks the electrons in, creates a triple bond, and there's my positive fragment. All right, so I'll bring the calculator up. I'll add them up. 16, 12, 12, 2, 12, 3. I get another 57. All right, and that's not the only way that they can cleave. We just now learned that. The other way is Mec Lafferty. So the true alpha carbon is really going to be here. So this is the functional group. That functional group is attached to the carbon. That's the alpha carbon. And we have alpha, beta. Mec Lafferty cannot happen here. Same thing on this side. Alpha, beta. Mec Lafferty cannot work. So it looks like really the only kind of fragment that I can get number-wise is a 57. Probably other fragments that are there. Based on what we've known so far, those choices don't exist, but there are probably more out there. But on the rules of ketones, 57. There's my number. All right, now let's take a look at the second one. In the second one, I do the same thing, right? Here's my C double bond O. I cleave on this side. This piece goes away. This gets my positive. I need to take the formula weight of that fragment. So I do a 16, a 12, a 12 and a 2, a 12 and a 2, and then a 12 and a 3. And I get 71. All right, that's good. That gave me a different fragment than what I got from my first one. So that could be an identifier, or helps me identify at least. All right, so let's get rid of all of this. And let's try this again. Instead of on the left, I'll do the one on the right. This piece goes away. Create a triple bond. And there's my positive. I'll bring up my calculator. I have a 16, a 12, a 12, and a 3. And I get 43 as a fragment. Now, this is a ketone, so I need to keep in mind ketones can do Mec Lafferty if it's present. So there's the carbonyl right here. This is the true alpha carbon. Nothing really is going to happen on that side. I'm not going to pay attention to it. On this side, here's the alpha. There's the beta. And here's the gamma. So Mcclafferty rearrangement can happen. Meaning that one of these hydrogens can be pulled off and it can be slapped here. So instead of a CH3, that's now a CH2. The bond between the true alpha and beta is going to be cleaved at that position. This goes off as a C double bond C with enough hydrogens on each end, CH2s, to be happy. So this goes away. Now what we're left with as a fragment is a CH3 group, carbon, double bond OH up here at the top, with another CH2 group that was there. That's where the bond was cleaved. And this thing is going to carry a positive charge with it. All right, so up here, let me bring up my calculator. I'll do the fragment weight of that. So 16 and 1, 12 from the double bond. And then I have 12 and 3 on one side and 12 and 2 on the other side. That gives me a 58. So I'm going to have to add that to the list. And I'm going to put here Mcclafferty Rearrangement, just so we know where that fragment was coming from. All right, so let me erase all of this scribble. And we'll move on to the third one. All right, so with this third one, same kind of deal. Here's my C double bond O. To the left, I can cleave that off. This goes away. A triple bond gets formed. There's my positive fragment. Bring up the calculator. I have 16, 12, 12, and 1. Then I've got that methyl group hanging off of there. So that's 12 and 3. And then finally, the last 12 and 3 that's in the chain. So that gives me a total of 71. Well, that's not really going to distinguish those two apart from each other. They both have a 71. This one does not, though. So that's good news. That one's going to be the easy one so far. All right, so I'm going to get rid of that. We're going to try on the other side. We're going to cleave it here. So this piece will go away. Triple bond gets formed. There's my O+. All right, I'll add up that weight of that fragment. 16, 12, 12, 3. That gives me a 43. So I'll add that to the list. Well, this one's got the 43 as well. So far, we got some problems. There's nothing different in it yet. And now we look at our final way that we can do this, and that is the Mcclafferty rearrangement. So I'm going to circle that area just so I understand that's the functional group, really. The true alpha carbon is right there. It ends. It can't go any further. This is the alpha carbon. That's a beta. I can't get to a gamma. It's got to be a straight chain, right? I've got to be able to go alpha, beta, and then there should be something right beside of that, which would be gamma. Well, it's not present. And then if I go down this way, that's the alpha. This is the beta. And it stops. So no Mcclafferty rearrangement is going to happen here. That's because I do not have a gamma carbon in order for that rearrangement to take place. So now this is kind of a clear-cut picture. If I look at the fractionation pattern or the fragmentation pattern, this first one would give me a 57. No other ones have given me that. These two have something in common. There's a 71 and a 71, a 43 and a 43. The difference is that that's the only two that this one would carry with it. The 71 and the 43, that's it. This one, though, has an extra way to fragment, so it has an extra number that it brings along to the table, and that is a 58. So let's take a look at the MS. Here's one of them. Now, this peak, huge, at 43. I'm going to go back to this slide, and I see, oh, look, here's a 43, there's a 43. So it's probably one of these two compounds. I just don't know which one it is. I look at the other numbers that are present. I see a 58. Is there a way that we got a 58 here? Yeah, there is. Look, right there's a 58 number. We see it. It's right there. What about the 71? And yes, you just heard my cell phone if you're wondering. All right, so here's the mass spec. We circled this 58, and we said 58 is coming from this Mec-Lafferty rearrangement on us, right? So here we see also a 71 and an 86. Now, the 86 we did not pick up yet, okay? But we did pick up the 71s. So for the most part, right now, as we see it, this does have the 43. We picked that one up. This does have the 58. We have that one. This does have the 71, and we have that one. Can we do an 86 number? Well, let's go back and take a look at our compound. If we did the entire formula weight of the compound, because we never did do that, right? We just did fragmentation pattern weight. So we'll do 12 and 3, 12 and 16, 12 and 2, 12 and 2, 12 and 3, we get an 86. So that's where that is coming from. So 43 is the base peak. That is the most stable fragment. 86 is the M peak, which means that this one is this structure. If we had to name it, again, I wouldn't require you to do this on a test, but review of organic, 1, 2, 3, 4, and 5. So this is a pentane. Normally, they're all single bonds. We erase the E, and we put -one to represent ketone. And then at carbon number 2, carbon 1, carbon 2, that is where we have the double bond O, which represents the ketone. So this is 2-pentanone. That is the middle molecule that we just now worked with. That's the fragmentation pattern. It matches up pretty well, so I can kind of comfortably say that that probably is the mass spectrum for that particular compound. 43 is the base fragment, or the base peak. So let's kind of go back and remember how we got that number. We cleave the bond here, right? And we've got 12, 12, 16, and 3. So again, if it had a choice, this gets a negative side or this gets a negative side, the negative is more stable with a larger fragment. So the molecule prefers to cleave on this side to allow this piece to go away with the negative. It's bigger, it's on its own, and this is what gave rise to that 43 fragment. All right, let's take a look at the other spectrum. Here's the other one. Here we see a 29, a 57, and an 86. All right, so 57 showed up on there. 57 was the base peak on there. If I go back to my choices, the only one that really gave me a 57 was this first one. And the rules of organic, 1, 2, 3, 4, 5. So this is a pentane. Drop the E, add -one, because it's a ketone group, and at carbon number 1, 2, and 3, you have the ketone group. So 3-pentanone would be this structure. So I'm going to write that up here at the very top. This is representative of the first one that we did. We also received a 29, and we also received an 86. Again, we did not pick those up. Where those are coming from, well, the 29, who knows? But let's do a molecular weight for this compound. So 12 and 3, 12 and 2, 12 and 16, 12 and 2, 12 and 3. There is our 86. So again, 57 is the base peak, 86 is the M peak, and 57 is the most stable fragment. Again, the way that we got that, we cleaved on one side. It was the same no matter which side we cleaved. This piece received the positive, and that gave us the 57. So that means that probably we have one more, and this one more could be given to the other ketone. However, that's where the problem stops. All right, so this is a completely different product or completely different problem. What has happened here is that they told us identify the ketones responsible for the mass spectra in 12.9, right? So here is 12.9, and this is basically where those numbers are coming from. So they gave you 3 compounds, but they only gave you 2 mass spectra to identify, because once you identify the 2, then you know what the third one's going to be. So that one's the reason that that kind of stopped. All right, let's take a look at another example. This is kind of following up the ketones, and it says 2 products are obtained from the reaction of 2-pentene with water and a trace amount of acid. The mass spectra of the compounds are shown in figure 1210. Identify the compounds responsible for the spectra. So the problem that I have with this is that this is mixing a little bit of organic with mass spectroscopy. And in a normal organic course or instrumentation class, I would have put this problem in your lap and I would have told you to solve it, because we have talked about organic reactions at this point. The 2-pentene. Pentene is a 5-carbon chain. 1, 2, 3, 4, and 5. On carbon number 2, we see a double bond that gets formed right there. And then this is the Z notation. Z groups are on Z same side. So this is really like a cis. That's how I've always remembered that, right? Z groups are on Z same side. You got to kind of bring out your German or Russian in a way. Here is our structure. This is a cis. It's a 2-pentene. We add water with a little bit of sulfuric acid. In organic chemistry, what you'll realize is that this is a way that we break the double bond. 1, 2, 3, 4, 5. 2 sites of addition open up, and the acid is a catalyst that will allow an OH from the water to go on and an H to go on. So one of these will receive a hydrogen and one of these will receive the oxygen. However, it's not really controlled, meaning that when this double bond breaks, the OH group could go here on carbon 3 or it could go there on carbon number 2. So we really do have 2 products, and that's what the reaction's saying. 2 products are obtained from this reaction. So here's the mass spec that we got from the product. Which one is basically responsible for that mass spectrum that we're seeing? Okay, well, this is an alcohol, and we said that alcohols have a tendency to break, and that has a tendency to break at the alpha carbon. So over here to the side, I'm going to start writing down some of the fragmentation patterns that we might see. I'm going to kind of clean this up a little bit first. So I could cleave it here. This piece would get a double bond, and this would be my positive side. So with this 3-butanol, or 3-pentanol, sorry, there's my fragment. A 12, a 16, a 1, a 12, and a 12 gives me 53. If I cleave it on this side, it's going to give me the same thing. A 16, a 1, a 12, a 12, a 12. Oh, wait a minute. Let me redo this because I fell for my own trick. I'm just going to rewrite this whole thing all over. 1, 2, 3, 4, 5. Carbon 3, I have an OH. But what I left off here with were the hydrogens. So let me fill those in, just so we don't forget them. And now let's cleave it at the alpha carbon like we did before. A double bond forms. We get a positive charge. And now let's just recalculate to make sure this is right. So I get a 16 and a 1, a 12 and a 1, a 12 and a 2, a 12 and a 3. And that gives me a 59. So I get a 59 here. And look, there's a 59. I'm on the right track. Over to the left-hand side, if I cleave it there, or to the right-hand side, if I cleave it there, same kind of deal is going to happen, right? Same weight, no difference. In the second product, I could cleave it here. Well, I'm not going to draw the hydrogens this time, but I want you to know they're there. This is going to be a 16 as well as a 1, a 12 and a 2, a 12 and a 2, a 12 and a 2, a 12 and a 3. So this gives me a 75 peak to show up. And then if I cleave it on this side and form the double bond, well, we can do the fragment weight of that one. The fragment weight of that would be 16 and 1, 12 and 2, 12 and 3. And that would be a 46. Based on this spectrum data, it looks like this has not given me a 59 yet. This is alpha, beta, gamma. Remember, I can take away an 18 from the total. It's not really going to make a difference. So based on this mass spectrum, it looks like the product that I'm referring to here is going to be my CH3, CH2, CH, CH2, CH3, and OH right smack dab in the middle of the molecule. Again, fragmentation pattern, that's what it's all about. Now, if I go on to part B of the question, this is the other mass spectrum for the other product. Notice here, with the other one, we had a 59. This did not give me a 59, right? And I do not really see a 59 to show up on this mass spectrum at all, which makes me feel a little bit better about my choice. This one, though, also shows a 73. Notice that this could do a Mec-Lafferty rearrangement and this cannot. So I'm going to go back and I'm going to do a total formula weight of the entire thing, meaning that this is a 12 and a 3, a 12 and a 2, and then a 12, a 1, a 16, a 1, a 12, a 2, a 12, and a 3, and then I'm going to subtract 18 from that. Because if Mec-Lafferty rearrangement can work for an alcohol, it's going to rip off a hydrogen, and that OH and the hydrogen is going to go away, and water is going to be formed. Okay, well, if Mec-Lafferty rearrangement works, what I'm left with is a 70, give or take a little bit. All right, now I'm seeing a 73 number here. However, full Mec-Lafferty is going to break off some bonds and throw off some chunks as well. So that kind of thing I want to keep in mind, but I don't really even need to go that far. I don't even need to draw those structures because I know that this molecule is the only way that I can get to 59. So I've at least identified that one, which means that this product has to be matching this spectrum. So that's kind of where I'll leave that problem. If you want to do the full fragmentation breakdown here, you're more than welcome to. Again, the water can be pulled off of there. Rearrangement can happen. Who knows what will go on to get even these other fragments that we're not picking up yet, but that is a possibility. All right, so those are some more of the types of questions that you will see from this test and from these assignments. So I have basically ventured on for 42 minutes on 2 example problems. So I know that you're tired of hearing me. I know that this video should have ended a long time ago. This is almost a full-blown lecture if you sat into a class. But hopefully you've put me on 2 times the speed, or maybe not even listened to half of it because you already know all of the things that I'm giving you. And if so, then that's great. But 42 minutes in, we've talked about 2 example problems, and in the next video, we'll continue on with the theory of mass spectroscopy. I know, how much more can we give, right?